Okay, so number one, we have a cricket ball is hit so that as it leaves the ground, both the horizontal and the upward vertical component of its velocity is 15 meters per second. How far will it travel horizontally before it reaches the ground again? So we want to find out the horizontal distance that it will travel. So horizontal is the x-axis, so dx. So that's the equation for that is equal to the velocity in the x-axis in the horizontal direction multiplied by the time that it's going for. Okay, and so we know that the horizontal component of the velocity will be 15 meters per second. So Vx is equal to 15 meters per second. And so what we need to find out is the amount of time that the ball was in the air for. Okay, so the way we're going to use that is by using the vertical component of the velocity. So the initial vertical component, the vertical velocity was, so Vy was equal to 15 meters per second, and that's the initial velocity. And when it gets to the top of its motion, the Vy final will be equal to 0 meters per second. So when it's at its highest point, the vertical velocity will be 0. Okay. So from that we can determine that the change in velocity until it reaches the highest point, which will be halfway, right? So the change in velocity will be negative 15 meters per second, right? Because it's losing velocity, so it'll be negative. So then you have this equation here, which is the change in velocity is equal to the acceleration multiplied by time. Okay, and so we know that the acceleration will be gravity. So acceleration will be negative 10. We're going to rearrange this for time. So time is equal to delta V over A. So time is equal to the change in velocity, which is negative 15, over the acceleration, which is gravity, which is negative 10. So the time that it takes for it to reach the halfway point, which is when it's going to be at the highest vertical point, is 1.5 seconds. So the total time because we'll assume that there's no air resistance, so it's going to be a symmetrical motion. So then it'll take 1.5 seconds to get to the halfway point, and then 1.5 seconds to come back down again. So then the total time in the air is going to be 3 seconds. So 1.5 seconds times 2, that's 3 seconds in the air total. So then the total distance in the horizontal direction is equal to the horizontal velocity, which was 15, times 3. So that's going to be 45 meters. Okay. Number 2, an arrow is fired horizontally at 30 meters per second from a height of 80 meters. At what speed will it hit the ground? So it's similar to that stone question that we had in our first tutorial, in the basic tutorial. So we've got an arrow. Its horizontal velocity is 30 meters per second, and it's going to come down and hit the ground eventually. So we want to find what the speed will be when it hits the ground. So when it hits the ground. Oh, thank you. Did someone, if you need more worksheets, they're over here. And the staplers, yeah, there's a stapler here as well. Cool, so we know that there's no air resistance, so this horizontal component of the velocity will remain the same. So we know that the horizontal component will be equal to 30 meters per second. And now we need to find out what the vertical component, so Vy, what the vertical component of this velocity will be. So again, we're dropped from a height of 80 meters and there's no air resistance, so the kinetic energy when it hits the ground will be equal to the potential energy that it had when it was at a height of 80 meters, right? So we're just going to use that equation. The velocity at the bottom is equal to the square root of 2 times gravity times height, and that's going to be 2 times 10 times 80. Okay, and so that's 40 meters per second. So our vertical velocity when it hits the ground will be 40 meters per second. And so then the speed which it hits the ground with, our V total. So V total is equal to the square root. So we're going to use Pythagoras, 30 squared plus 40 squared, which will be 50. Okay. And just realize that there's going to be different ways that you can do these questions. So don't worry if you've used a different way, or if you think of a different way to do these questions. Okay. So there's going to be lots of different ways that you can do these. Number 3, a car traveling at 15 meters per second hits a power pole. If the 60 kilogram passenger is uniformly brought to rest, so when they say uniformly brought to rest, what that means is the acceleration is constant. Okay. She's brought to rest by her seatbelt in a distance of 0.3 meters. What is the average restraining force required in newtons? Okay, so I'll show you 2 ways that you can do this. So first of all, you can calculate the time that she was, so what we want is the force, right? So we want the force. So the first equation that we can use is the change in momentum is equal to the average force multiplied by the time that it was applied for. Okay, so this is the change in momentum because she had a velocity at the start and then she was brought to rest, so there's going to be a change in momentum, right? So we want to know the average force. So we're going to rearrange this for average force, which is equal to the change in momentum over the time. And the problem here So we can calculate what the change in momentum is going to be. So change in momentum is equal to final momentum minus the initial momentum. So final momentum is mass times final velocity minus initial momentum, which is mass times initial velocity. So we'll just factorize that. So that's mBF minus VI. Okay, so mass is 60. 60 times final velocity is 0. Initial velocity is 15. Okay, so 60 times negative 15. So that will give you a change in momentum of 900. So negative 900 because she's lost momentum. Negative 900 kg meters per second. Okay, so now we need to calculate the time that she took to come to rest. So we're going to use distance is equal to the average velocity multiplied by the time. Okay, so she had constant acceleration, so V average is equal to VI, the initial velocity, plus VF divided by 2. So remember, if you have constant acceleration, the average velocity is going to be the halfway point. So she had a change in velocity of 15, so her average velocity will be 7.5. So average velocity during the time that she came to a rest will be 7.5. So that would just be 15 plus 0 divided by 2, which is 7.5. Okay, so average velocity of, and then, so here we're looking for the time. So we're going to rearrange for time. Time is equal to D over B average, which is, so the distance we were told is 0.3 meters. And the average velocity was 7.5, which is equal to, so that's 0.04 seconds. So that's 40 milliseconds, right? So that's a very short time, right? It just shows you how much, why these collisions can be so devastating if you're in a car crash. Okay, so you've gone from 54 kilometers per hour to 0 kilometers per hour in 40 milliseconds. Okay. So then you've got your time and you've got your change in momentum. So average force is equal to the change in momentum, which is negative 900 divided by the time, which is 0.04. And the average force will be 22,500 newtons. Okay. Right. So that's a huge amount of force, right? Okay. So that's a bit of a long way to do it, but I just wanted to go through it, so it's a good way to remind you of the change in momentum, right? And how to use it, and all these different equations as well. So I just wanted to go through it the long way to try and illustrate all of these, but in the exam you'd probably do it another way, and I'll show you that now. So the short way to do it is just to find the acceleration. So the average acceleration So acceleration is equal to the final velocity squared minus the initial velocity squared over 2 times the distance. So this equation is on the cheat sheet that I have. And you guys, if you haven't made your cheat sheet already, you should really get onto it as soon as you can and then start using it. So our final velocity is 0. So 0 squared minus the initial velocity, which was 15. 15 squared over 2 times the distance. So 2 times 0.3. That will give you negative 375 meters per second squared. Right, so that's your acceleration. And then the force is equal to mass times acceleration. So that's just mass of 60 times negative 375, which will give you 22,000, so negative 22,500 newtons again. Okay, so it's negative because it's working in the opposite direction. It's working backwards. Okay, so that's a bit simpler if you just found the acceleration. Doesn't matter which way you do it. Okay, so number 4, we have a 12 meter long 30 kg wooden plank lying flat on the ground. If one end of the plank is to be lifted by a vertical force applied 2 meters from that end, what minimum force will be required? So you're going to draw your plank, and then we're going to apply a force 2 meters. So we're trying to lift this end, and we're going to apply a force 2 meters from that end. So our force will be here, and the distance will be 2 meters from this end. And because the plank is 12 meters long, that means it's going to be 10 meters from the other end, which is our fulcrum. Okay. All right. So we'll place the fulcrum at the other end. And then, of course, we need to put in the force, the weight force of the plank. So that's going to be acting in the middle of the plank. So that's going to be 30 kgs mass. So that's 300 newtons downwards. So that's the weight of the plank acting at the middle, at the midpoint. So the distance there will be 6 meters, okay, from the fulcrum. So again, you're just going to say that the torque clockwise is equal to the torque counterclockwise. So this force here, let's say is F1. So this is F1, and this one is F2. So F1 is going to make the plank rotate clockwise, and F2 is going to make the plank rotate counterclockwise, so upwards. So that's F1 D1 is equal to F2 D2, and we want to find out what D2 is going to be. Oh, sorry, what F2 is going to be, this force here. So we're just going to put our numbers in. So force 1 is 300, times the distance, which is, so that's, this force here is 6 meters. That's equal to force 2, which we don't know. Force 2 times the distance, which is 10 meters. So that's 300 times 6 is 1800. 1800. Yeah, 1800 is equal to 10 times F2. So then 180 is equal to force 2. So that's your answer, 180 newtons. Okay. So that's pretty simple. This one should have been in the basic tutorial. Okay, so this next one's a little bit tricky. We have a small metal puck sliding along a frictionless horizontal rail with a velocity of 0.5 meters per second, and the rail begins to curve upwards. When the height of the rail has increased by 8 millimeters, how fast will the puck be traveling? And you're going to assume that no energy is lost to friction or air resistance. So we have a change in height. So the change in height is equal to 8 millimeters, and remember that has to be in meters. So 8 times 10 to the negative 3, or 0.008 meters. So remember here we're gonna, if we gain height, we're gonna lose potential energy, right? And sorry, my bad. If you gain height, you're gonna gain potential energy and you're gonna lose kinetic energy, right? So the change in velocity is equal to the square root of 2 times gravity times the change in height. So remember that equation when kinetic energy is equal to potential energy. So this time we've just added delta to it. So the change in velocity is equal to the change in height, or proportional to the change in height. Well, actually proportional to the square root of the change in height. So if we put our numbers in, 2 times 10 times 0.008. So our change in velocity will be 0.4 meters per second. And so if it goes upwards, it's going to lose kinetic energy. So it's going to be going slower. So our final velocity is equal to the initial velocity, which was 0.5 minus the change in velocity. So that's 0.5 minus 0.4, which is equal to 0.1 meters per second. Six, 5 identical cubes of lead are stacked in a single column on a table surface to make a tower. Each cube has sides which are 44 millimeters long. What's the gauge pressure between the undersurface of the tower and the surface of the table? So this one's a little bit hard to interpret, but basically what they're saying is you've got 5 cubes, 1, 2, 3, 4. You've got 5 cubes stacked up like this. Yeah. So you've got 5 cubes stacked up. And so it's sitting on the table surface. So you want to find the difference in pressure between this point, between the underside of this tower and the pressure difference on the table that's not under the tower. So basically what you're going to do is you just need to find the amount of pressure that's being exerted by this column. So we're going to use our equation. Pressure is equal to force over area. All right. And so force is going to be, so that's, the force is going to be the weight force of these cubes. So force is going to be mass times gravity over the surface area. So because it's a cube, area is going to be length times the width, right? So area is length times width. Okay, and we know that each side is 44 millimeters long. So we need to find out what the mass of this tower is going to be. But we don't know what the mass is. We only know the density of the lead. And we can calculate the volume of this tower. So mass is equal to density times volume. And so the density is 11,340. So times the volume. So the volume is going to be the length, which is 0.044 meters, times the width, which is also 0.044. So we can just say 0.044 squared. Okay, so that's length times width. And then now the height will be 0.044 times 5, because there's 5 stacked up high. So that's 5 times 0.44. Okay, so that, yeah, so which will be, so that'll be 0.22 meters, the height. So length times width times height, and the height is 0.22. So that will give us our mass, which is 4.83 kilograms. So now we can go back to our pressure equation. Pressure is equal to force over area. And the force is going to be 4.83 times 10, which is 48.3. Over the area, which is length times width. So that's 0.044 squared. And that will give you 24,948, which is the same as 25 kilopascals. So yeah, quite a few steps involved in that one. Number 7, we have a toy boat floating in water, which displaces 0.31 meters cubed of water. The same boat floating in an unknown fluid displaces 0.39 meters cubed of this fluid. What's the density of the unknown fluid? And we've been given the density of water, which is 1,000. So 1 times 10 to the power of 3, that's 1,000. So here, we don't know the volume of the boat. But if we did know the volume of the boat, it would be helpful. So we're just going to give the volume of the boat as 1 meter cubed. So we're going to set the volume of the boat is equal to 1 meter cubed, and that's going to help us to solve this problem. Okay, so whenever you're not given a variable, you can kind of just allocate a variable to allow you to solve the problem. Okay, so that's an option for you. So we'll say the volume of the boat is 1 meter cubed, and when it's floating in water, 0.31 meter cubed is underwater. So that means that 31% of the boat is underwater. So in water, 31% is underwater or submerged, because it's displacing 0.31 meters cubed of water. So what does that mean about the density? So what will the density of the boat be? So the density of the boat will be equal to 31% of the density of water. Yep, so 0.31 times 1,000. Yep. So 31% of 1,000, which is going to be 310 kilograms per meters cubed. Okay. So the density of the boat, because we said that the volume of the boat is 1 meter cubed, now we can say that the density of the boat must be 310 kilograms per meters cubed. Okay, so it's important to note here that this isn't the actual density of the boat. It could be anything, but if the volume was 1 meter cubed, then this is what the density would be. Okay, so you could have given this any number and it would be different. Okay, but we're just trying to solve this problem here, and that's just the best way to do it. So now we've figured out the density of the boat. So now we need to figure out the density of the unknown fluid. So we know that in the unknown fluid, so now in the unknown fluid, 39% is submerged. So what that means is that the density of the boat is equal to 39% of the density of the unknown fluid, right? Because 39% is underwater, so that means that the density must be 39% of the unknown fluid. So then if we want to put this in a mathematical form, that'd be 0.39 times the density of unknown. Okay, so what we want to solve for is this unknown, the density of the unknown liquid. So we're going to rearrange it. So density of unknown is equal to the density of the boat divided by 0.39. So the density of the boat, we said it was 310 divided by 0.39. And that's 794.9 or 795. Okay, and there's going to be, there's different ways to solve this problem. So yeah, don't be too worried if you used another way, if you tried it. Number 8, a non-viscous fluid with a density of 1670 kilograms per meter cubed flows through a horizontal pipe. So if it's horizontal, the height isn't changing. So H1 equals H2. At the inlet, the cross-sectional area is 0.1 meters squared, and the velocity is 20 millimeters per second. Downstream at the outlet, the pipe diameter contracts to half the inlet diameter. Okay. So we want to find out the volume of fluid that's discharged from the pipe in 500 seconds. So first of all, I'm going to draw this pipe. So we have this pipe. Okay, so the diameter so the diameter at point 2 is half of the diameter at point 1. Okay, so you need to understand the relationship between area and the radius. So if the diameter is halved, it means the radius is also halved. Okay, so area is equal to pi r squared. So if you halve the radius, it's going to be, so you're going to, if you decrease radius by a factor of 2, area is going to decrease by a factor of 2 squared. Okay, so the cross-sectional area at point 2 is going to be 1/4 of the cross-sectional area at point 1. Okay, so I'll just work that out for you. So A1, and the reason that you want to know what the cross-sectional area is because the velocity is going to be inversely proportional to the area. So it's going to be going faster when it gets to this narrow point. And if you know that the area is 1/4, has decreased by a factor of 4, then you know that the velocity will increase by a factor of 4. Okay, so V1 here is equal to 20 millimeters per second, so that's has to be in meters, so 0.02 meters per second. And the cross-sectional area, so A1 is equal to 0.1 meters squared. Okay, and yeah, so at point 2, so we know that the radius is going to decrease by a factor of 2, so the area is going to decrease by a factor of 4, which is 2 squared. So A2 will be equal to A1 divided by 4. So that's 0.1 divided by 4, which is equal to 0.025. So that's 0.025 meters squared. Okay. And if the area, the cross-sectional area is 1/4, the velocity at point 2 will be 4 times greater. So V2 will be 4 times 0.02, which is 0.08 meters per second. Okay, so we figured out the velocity at point 2. So we actually didn't need that for question 8. So we need that for question 9. So now we'll focus on question 9. What volume of fluid is discharged from the pipe in 500 seconds? So for this question, you'll know that flow rate is equal to volume over time, or the change in volume over time. And that's also equal to the cross-sectional area multiplied by the velocity. So here we can just use these two equations. So we'll get rid of the flow rate. So we have the change in volume over the time is equal to area times velocity. Okay, so what we want is the volume of fluid. So we're going to rearrange this equation for just volume. So volume, the change in volume is equal to area times velocity times time. So delta V is equal to the area, which is, so we can use either one, because remember the flow rate at every point in the pipe is going to be the same. So let's just use A1 and V1. So 0.1 meters squared times V1, which is 0.02, times the time, which is 500 seconds. And that will give you 1 meter cubed. Okay, so your answer is 1. And then now question number 9. So we're continuing on from that. What's the difference in pressure between section 2 and section 1? So you're going to use that long equation. So P1 plus rho GH1 plus half rho V1 squared is equal to P2 plus rho GH2 plus half rho V2 squared. Okay, and because the height's the same, we can get rid of the rho GH1 and rho GH2. So we're going to get rid of rho GH1 and rho GH2 because it's a horizontal pipe, which means the height doesn't change. So what we want is P2 minus P1. So P2 minus P1 is going to be equal to half rho V1 squared minus half rho V2 squared. So rho, this here is density. Okay. And if we wanted to, you can just factorize that to make it a little bit easier. So half times the density, or rho, V1 squared minus V2 squared. Okay, so that's just factorized. 0.5, which is half, times the density, which is 1670, and multiplied by V1 squared. So that was 0.02 squared minus 0.08 squared, and that will give you negative 5.01 pascals. So that's your answer. Okay, so just understand that relationship between the radius and the area. If the radius doubles, the area is going to change by a factor of 4, which is 2 squared. Okay. Number 10, to finish building a barrel, you need to place a solid steel ring over the top end. The top of the barrel has an outer radius of 30 centimeters. The steel ring has an inner radius of 29.9 centimeters at a temperature of 10 degrees Celsius. To what temperature must the ring be heated in order to fit over the top of the barrel? And we want that in degrees Celsius. So what we need to do is we need to find the final temperature. So we want to find, final temperature. And to do that, we're going to find the change in temperature that's required. So we're going to use, so here this is going to be, we've been given the linear thermal expansion coefficient. So this thermal expansion, the change in length is equal to the original length times the